Alright, so good night, guys. Okay, let's start by at the beginning. This problem, I have no idea. Yeah, I know why this works because because s times s plus 1 always gets an even number. For example, 2 times 3 gets 6, and an even number divided by 2 is an integer, so, or integer, I'm not sure how it's pronounced. So yeah, that is why this specific example works. Then they convert this to the specific notation like here, and that's it. I don't know anything else, like I don't know. Now to the harder problems. Exercise 23, I kind of already did it. They asked me to show that there is a 1-1-1 correspondence of s onto t, and the function is 2 elevated to m times 3 elevated to n. And it's because it's a prime, they are both primes in this case, elevated to something, and multiplying primes, or like multiplications, or multiplying primes elevated to something will always get another prime. So yeah, that is why it's a one-on-one, because you can't repeat this with any m or n. Exercise 24, well, I didn't do this, but it's like any positive integer will be like one positive rational number. So yeah, I think that's it, I'm not sure. Exercise 25, find the they ask to find a function that goes f of s plus 1, f s1 plus s2 gets us fs1 times fs2, and they even say from all real numbers to the set of all positive reals. So this really implies to use the exponential function. Oh, sorry. Yeah, this is where I began. First I tried the logarithm, then realized that the function is the other way around. We went the other way around. So I tried with exponential, and I tried an example, and it worked out fine. Now I'm confused, well, not confused, but I want to know if there is like a way to get to this exponential function from just this, because I've read some apostle like last year, I think, from when I was doing calc 1, and I kind of remember this, that I think he defined e or exponential, yeah, when every time I said exponential this video, I meant e. So e elevated to something, that number e, well, a number can't be a function, but what I'm trying to say is e elevated to, wait, I forgot what I was going to say. So yeah, Apostle defined e as a number that when elevated to like a sum of numbers, it could be defined as the multiplication of those numbers by e. Well, what's in here? I'm having trouble to express my thoughts, I guess. So so he defined e as the function that did this, and I'm not sure if we can get to there from here, from just getting a function from this exercise. So exercise 26 explicitly, I'm not sure if I did this explicitly or if I could do this more explicitly. So what I did is f of s is eta elevated to s, then we do the inverse of fs, which has to be s. So inverse of f of elevated to s has to be s. So I just substituted f inverse of f to log. I'm not sure if I can be more explicit than this, but yeah. So next I did exercise 27a, and alright, wait, let me check how long is this. Alright, 5 minutes and 30 already. F and G are mappings of S into S, and F after G is a constant function. Then, what can you say about F if G is onto? Well, I'm saying here, if G is onto, so G of set S has the same this is crossed out, has the same number of elements as S. And if f after gs is a constant function, then f is a constant function. I found that there is one exclusive exception to this, that if s only has one element, because then f doesn't necessarily have to be a constant function, just has to be any function. Exercise B, what if f is 1 on 1? Well, by the definition of f s1 of what 1 on 1 means, I saw that this doesn't happen because the function it gives a constant function, so it must mean that s1 equals s2, so g is a constant function because it gave us that input into f. After that, exercise 28, which asks, yeah, I forgot to mention that I read this part. I haven't tried the problems yet, but this only talks of 1 into 1, and I realized that that must mean that if it's 1 on 1 and it maps to itself, then it must also be onto itself, onto. So yeah, I realized this before I did this exercise, and so yeah, it felt like easy, or I was prepared because I thought about it. So here is my solution. Yeah, I just read this, I guess. For exercise 30, I couldn't do it. I think this is wrong, or maybe my definitions are wrong or something. So it says S is a finite set. F is 101 mapping of S. Show that some integer n bigger than 0, that you can have f, and it will eventually get to the identity. So s equals s, for example. So what I did was, this is the question. Wait, no, not this one. Sorry. Yeah. So I think I don't understand. And the main problem is f, they say that the function is S is a finite set and f is 101 mapping of S. So we know that it comes from S, and 101 oh yeah, before that, so if we have to, for us to be available to do this, then the result of this has to be inside of S. Otherwise we can't define a function f that acts on S if an element that we want to act on isn't on S, or at least, like, I don't think it's legal to do that, or probably the result should be undefined, I think. So from that we know that S must be onto, F must be onto. Wait, no. Well, one of my questions is, if we say that f is a mapping from S into itself, does it mean that it is onto itself? Because if it isn't, then we can say that this f of S is inside of S, but the f of big S, or which I mean set S, is also contained inside of S, but isn't equal to S because it isn't onto. So my problem becomes, let's say we have a set 1 to 5 and the function f is s plus 1. Then we know that, for example, f of 1 equals 2 and so on. So the function will be one-on-one because every result of this function will be different for each input. But then it won't be onto. And I think, well, yeah, for the way that I was thinking to resolve it, we would have it to be onto. And because we do f of s, then it has to be onto, I think, to be able to do this. So yeah, I'm not sure if I really understood this problem. And exercise 31, I also think that I don't get it, but maybe another day for this one. So yeah, thanks for watching, guys. Goodbye.